Hey guys, in this video we are going to cover integration, specifically integration by substitution and integration by parts.
So now we have taken a look at how to solve this expression in the way that I did, but now I'm going to change a little bit the expression in order to show another way of solving certain kind of integrals. What we're going to do is we are going to take this part over here, which is 3x plus 1, and we are also going to name it g, as the example from before. And we are also going to differentiate it. So dg dx is going to be 3x differentiated is 3, 1 differentiated is 0, so I'm just not going to add. And then we just follow a very similar procedure, which is we exchange the dx with the 3. So this is dg over 3 equals dx. And then, because we already have an expression for dx, we just substitute in there. So this is the same as saying the integral of, because this 2 is just a 2, I'm already going to leave it outside. So this is e to the power of this part over here, which we said it was going to be g. And then differential of x, we just write dg over 3. So times dg over 3. Now, this is technically dg times 1/3. 1/3 is a constant, so it can go away outside of the integral. So it's dividing the 2. So we have 2/3 over there. And then we just have e to the power of g times dg. So this is just a simple integration. So 2/3 of eg plus the c, which is the same as changing the g and putting it back to its original form. So 2/3 of e to the power of 3x plus 1 plus the constant, and that's the second solution to the exercise. So we have taken a look at how we can integrate by substitution, but the way that integration by substitution works is by taking advantage of how the structure actually is inside the integral and how we can use it to simplify the expression. However, we will not always have this, and then we just have to go the hard way about it. And the hard way about it is called integration by parts, which is basically following that formula over there. So what we need to do is, for using this formula, we need to take a look at what we have inside the integral, and then we have to notice that we have something that is called u and something that is called dv. So what we want to do is we want to choose what u and what dv is going to be, so that the resulting expression is going to be as simple as possible. For that, we have a certain kind of priority choices, which is called x-lipet. X is just for x, like the normal x, logarithms, inverse trigonometry, polynomials, exponential, and trigonometry. The way it works is we use this priority to choose what our u is going to be. So we start from the top, and whenever we reach something that is already inside our expression, we choose that to be our u. So in this case, we see that we already start with x. We have an x, so that's going to be our u. U equals x. And then whatever is left inside the expression, we just choose it as to be our dv. So in this case, dv is going to be sine of x. Now, you may notice that as we go on in the formula, we will have to deal with du and also with v. So I suggest that when you're going to use this formula, you calculate this first, so then you just have to plug in the values in the expression. So then du is going to be the differential of x, which is 1, and v is going to be minus cosine of x, because it's essentially the integral of the sine of x. So what we have to do now is just plug in the values. So integral of u dv dx is going to be u times v, so u times v, x times the minus cosine of x, minus open integral v is minus cosine of x, and the u is going just to be 1, so I'm not even going to bother writing it, dx. And now it's just like simplifying stuff. So this is minus x times cosine of x, minus and minus become a plus. The integral of the cosine is going to be the sine of x, and because it's an integral, we must not forget that we need to add a constant, And this will be the solution to the exercise.